this length L is deduced from a pressure match. Okay, so how do we match pressure at this point here? So we know that we can get there from P naught in two ways, right? We can go across here, right? Cost us nothing. Cross up by the interface, step it across, and then go here, right? And then, so that takes it up to LC. We can also start here, go across, it costs us nothing to cross the interface there because there's no curvature, and then come down here, right?
So we're saying that the point where you match the static meniscus and dynamic one is 2 times h infinity?
Yeah.
That's an experimental fact? Or?
That's our definition.
Okay. Because I thought the static meniscus had to do with having the angle of contact at the end.
Yeah.
That's what's happening in this.
That's right. That's basically what's happening outside of here. So you have this limited. That's basically the balance of here, right? And then here, the viscous stress is important as you get close to the wall.
Sorry.
What's that?
If you can use
Oh, sorry, yeah. Okay, so in the zone 2, so in this upper zone, the curvature, you guys are hopefully getting comfortable with slapping down curvatures from looking at interfaces. Again, it's basically turn it upside down, it's hxx, right? So it's going to be scale is h over L squared, right? So h is our h infinity here. So if you want to write, maybe just to be clear, it looks like that. So, so the pressure match at A so we can, in jumping across the interface, so this is what we get by going along the bottom and up. So this is the hydrostatic pressure, and this we get from crossing the interface in zone 2. Okay? I kind of like scaling arguments because you're constantly questioning, is that right? Is that right? Is that right? And it seems very, this is quite an elaborate scaling argument. And you can contest every single statement. But one is ultimately justified if the scaling argument collapses the data. It is slippery. But I'm telling you, the match asymptotic expansions are a nightmare.
Yeah, so what Carlos was asking,
Huh?
so that 2h infinity is at 0.8?
0.8?
H infinity is at 0.8?
Yeah, so I'm imagining h infinity. So if you get far enough away, that's the final coding on the film, right? And so then you're assuming this is 2h infinity.
That's a little bit like...
Yeah. It's arbitrary, right?
Sorry. Well, first the thing is where you're going to match, the solution is a little bit arbitrary, fine.
Yeah.
But why 2h? Not 1.5h or 3h?
Well, then you just have a factor floating around in your scaling argument, right?
So it's the same thing as saying it's order
Yeah.
infinity.
Yeah, exactly.
It's of the same order.
Yeah, exactly.
Okay.
Yeah.
And then you adjust it.
Yeah,
Okay.
yeah.
That makes it
Yeah.
a little more systematic.
Yeah, right. Yeah, this really is, this is heavy-duty scaling argument, by the way. Like, I consider these French guys, I hope they aren't watching, masters of scaling arguments. But this one I was very impressed by, because I'd seen the full development, and the full development is awful. So,
It's a satellite broadcasting.
yeah, it's straight to Paris. Okay, so, right, so this gives us, this tells us basically what L is. So our length L, which is, as we said, is slightly arbitrarily defined, has a characteristic order, which is the geometric mean of the capillary length and the thickness, h infinity. Okay? So it's somewhere in between the two. I shouldn't have introduced h infinity, but so h is h infinity.
Drop infinity as
Yeah. Yeah. Infinity is 1. Okay, so right. So if we now look at the force balance in this region 2, then we have viscous stresses and curvature pressure. So you say mu u over h squared, so that's what we had before previously balanced it with gravity. Now we're going to balance it with the gradient and curvature pressure. So the gradient and curvature pressure is sigma h over L squared, and we need a gradient, so we divide by 1 over L, right? So that's the gradient and curvature pressure as you go from here to here, right? So it's basically the local gradient. One has a gradient of curvature pressure everywhere within this region, which is balancing the viscous stresses. Okay, because this is, of course, this is delta P over L. Okay, so if we substitute in for L, we're going to get a new scaling. So I keep changing on mu. Okay, mu. So we get the capillary number LC to the 3 halves H to the 3 halves. Okay. Gives us the following scaling. H goes as LC capillary number to the 2/3. So the important physics to get out of this is that what's resisting entrainment is this suction that we're getting from the meniscus, right? And so this changes the dynamics. So it's not simply the weight of the fluid, it's this capillary suction resulting from the surface tension. Okay, and so that changes the scaling, where again, so our capillary length and our capillary number is mu u over sigma. Okay, and this is consistent with data. Okay, this is the correct scaling. And so let's do the calculation. Jump out of swimming pool. So what's the thickness of the film which accompanies you? Say we jump out at 1 meters per second. So the capillary number, so mu, so for water, we have 10 to the minus 2 in CGS, 10 to the 2 for a meter per second, and around 100 for the surface sensitive water. So that gives us around 10 to the minus 2. So that gives us H on the order of 100 micron, which is about right. Right? It's not, you don't get a whole millimeter of fluid sticking to your body, right? Get something less than that. And then, so if you multiply by your surface area, and well, let's just say you've been to Port Cow recently, and it's 2 square meters. And so that you get around 300 grams of water.
I have no idea what my surface area is.
So that was right. So your estimate, you guys guessed about 2 of these, which is about right.
But that depends if you shaved your arms and legs and chest.
Yeah, that's right. And whether you've waxed recently, yeah. No. Oh no, we're being filmed. God. Right. Okay, so all right. So now let me tell you. Say, well, you guys are probably wildly unsatisfied with that. What a bunch of hand-waving scaling arguments that was. But let's look and see what the solution is if you do 2 weeks of mathematics. And on this one, I've got to side with the French to the detailed solution. And yields okay, so long-lived scaling arguments. Okay, so there are limitations. So if you look through this all carefully, in terms of this consistency of the scaling, yeah. You wouldn't even have time to go swimming. You'd be too lost in the mathematics. So implicit in the above scaling.
So if you're in a hurry, how fast after you leave the pool so you don't need a towel?
What's that? The faster you go? Yeah.
The faster you go, you wouldn't need a towel.
That's true. That's true. So we've assumed that H is much less than L, which is an indication that capillary number, the 1/2, has to be less than 1. We've assumed that L is much less than LC, which is also satisfied there, and we've assumed that rho G, so the characteristic gravitational pressure is less than the characteristic gradient in curvature pressure. And so these are all actually consistent with as long as the capillary number is much less than, the capillary number to the 1/3 is much less than 1. Okay? And so this is really saying that the capillary number is less than 10 to the minus 3. Which it isn't strictly speaking here, but that doesn't matter. We're just scaling. Okay, so other little twists on this. I've mentioned surfactants. Then we'll take a break. So again, these are important problems for fiber coating and other industrial processes. And whenever you do anything where surface tension is important, you're soon going to get some strange result that you don't understand, and it's because of surfactants, right? And so what does surfactants do here? Okay, so first off, we know that they decrease this, so they increase the effective capillary number, so that has a small effect. But we know that they also impart an effect of elasticity to the surface. So if this is our configuration, say we're pulling a plate out, then if we have a contaminated interface, right, then there's going to be, you're creating surface area, so there's going to be less surfactant here than here, right, which means you're going to have surface tension is going to be high relative to here, and so there's going to be an additional Marangoni stress, which emplaces fluid. So you're going to get a much thicker layer than you would if you had a clean surface. Okay, so again, principal effect. So these dashes are the little surfactant molecules. Again, if you're creating surface area, you're going to have a gradient in their concentration, which results in surface tension gradients. And these surface tension gradients we call Marangoni stresses. Okay, so this can cause the layer thickness okay, so typically double. So there's sorts of Marangoni, so it's in some sense doubling the stresses generated by the it's countering. So you have this capillary suction here, and this is being mitigated by the Marangoni stresses. So it's adding, contributing to the entrainment.
So for example, if I put soap on the surface of something in the pool,
yeah,
and I do that experiment quickly enough so it doesn't mix, this will rise to a thicker layer, right?
Yeah.
But then if the soap mixes, then it puts the
Well, the soap.
down, and then it might slide.
So what do you mean by mixing? You mean equilibrating on the surface or mixing through the bulk?
Through the bulk, because then
So the soap always sits on the surface, right? It basically wants all the molecules want to sit on the surface.
Won't there be a little bit of diffusion mixing?
Yeah, you can have some.
Diminish the viscosity and then it'll be more slippery. That's what I'm trying to think.
Yeah, so I mean, its role in the bulk is pretty negligible. It's basically changed the viscosity by some very small amount, but it has a huge effect on the surface dynamics.
So if you pull it, you're going to get a thicker film.
Yeah. And again, most fluids suffer from the influence of surfactants. The things that don't are silicon oils, which is why we use those in the bouncing drop experiments, for example. Okay, let's have a coffee.
Why do silicon oil?
Don't know. They're fortunately